Alright, conjugate addition will blow your mind. Here we go. So this is the enormity of what we have covered so far, and we will be summarizing all this at the end of this mini lecture because this will be our last Chapter 17 mini lecture. We'll talk about synthesis using all these wonderful new reactions we've learned in Chapter 17 in class on Valentine's Day. So you've seen this slide before. Actually, this is from the first mini lecture where I was introducing the key points of Chapter 17. So when we have a conjugated system, an alpha-beta unsaturated carbonyl, what we know is that we can draw two resonance contributors. This one, where the positive charge is directly upon the carbonyl carbon, or this one, where I use these pi electrons to push out the carbon-oxygen pi electrons to get the positive charge on this carbon. That carbon is the beta carbon because, as we already know, these right next to the carbonyl are the alpha carbons. So the bottom line is, for conjugate carbonyls, or conjugate polar pi bonds, we have two electrophilic sites in our system. The carbonyl carbon and the beta carbon, leading of course to two different reactions. Addition at the carbonyl carbon to give you the 1,2 product, or addition at the beta carbon to give you the 1,4 product. And as I mentioned in mini lecture 1, this means selectivity issues. So before we look at those in some detail, we really need to understand the mechanism for 1,4 addition, which means identifying our nucleophile and electrophile. So for 1,4 addition, our electrophile is the beta carbon. So the nucleophile is attracted to the delta positive on the beta carbon. The pi electrons are pushed up onto the oxygen, and we get a resonance delocalized enolate intermediate. And that's kind of an important feature of 1,4 addition. So how do we get from this guy to our product? Well, we've already seen some enolate chemistry. Recall that this can just push those pi electrons back in, and if you have a protic workup, as in H3O+, for example, all we have to do is protonate at the alpha carbon to get our 1,4 product. And I actually have the 1 in the wrong place. 1, 2, 3, 4 is what this should look like. So we'll ignore that. Ignore that. And put the numbers in the right place. 1, 2, 3, 4. Okay, so the problem with conjugate addition is that this guy can kind of go one place or the other. And as chemists and people who make new molecules, we want to know where that nucleophile is going to go. So when do I get 1,2? How do I get 1,4? All of those questions need to be addressed. They're addressed in Chapter 17 by 3 features. The concept of the reversibility of the addition between the nucleophile and the carbonyl. Is it reversible or irreversible? The concept of kinetic versus thermodynamic control, yet again, which we're kind of seeing over and over again. And I will introduce a new way to help you keep this straight, and that is the concept of hard versus soft nucleophiles and electrophiles. So, back to our resonance contributors. Table 17.2 on page 839 gives you a list of nucleophiles that will give you 1, 2, or 1,4. But that's not good. We don't want you memorizing lists. We want you to understand why one would be 1,2 and the other would be 1,4. So that's where hard-soft acid-base theory comes in. So if you look at this resonance contributor, you can see that the two charges are right next to each other. So they're really concentrated and localized right next to each other, and that makes this charge really kind of brutal, making this the hard, concentrated site where the charge is localized. On the other hand, if you look at this resonance contributor, you can see how the four charges are more definitely further apart, and you can kind of imagine them being diffused through this entire system. That makes this the soft site. Alright, so convince yourself one way or another that this is a harder, more concentrated, more hard concentration of charge, whereas this one farther away from the oxygen is a softer, maybe not as well developed delta positive. Bottom line is, this is the hard site, this is the soft site, and hard nucleophiles will react at the hard site and give you 1,2. Soft nucleophiles react at the soft site and give you 1,4. So what we're down to now is trying to figure out, well, what makes a nucleophile hard and what makes a nucleophile soft? Well, it's the same kind of game I'm playing up here in the yellow box. A soft nucleophile is not quite as highly developed. Alright, it's a less strong development of negative charge. So we know the halides, for example, are like iodide, big atom. That negative charge is really diffuse over a very large center. Oxygen, well, oxygen's certainly stronger base than iodide, for example, but it's, you know, the negative charge is on an electronegative atom, so that makes it a lot less concentrated, if you will. An even more quote-unquote obvious way to think of soft nucleophiles is to think of the fact that they could be delocalized. Alright, so enolates are classic examples of soft nucleophiles because the charge is delocalized across the oxygen and the carbon. So the bottom line here is that soft nucleophiles, which will react at the soft carbon of your conjugated system, are just a little less nucleophilic, a little more diffuse, a little more delocalized, a little milder, if you will, than hard nucleophiles. What on earth then is a hard nucleophile? Well, geez, something like H-, where that charge has no place to go. That would be a hard nucleophile. And certainly our organolithiums and Grignard reagents are definitely hard nucleophiles. Alright, so for example, if we have this conjugated enone, if I add a Grignard reagent to it, I know that nucleophile could either go to the 1,2 position or the 1,4 attack, but because this is very much a hard nucleophile, don't think that you can delocalize that negative charge, because you can't. It will definitely go 1,2, and upon workup with our aqueous acid, we will get the 1,2 product. This thiol, on the other hand, is a big old soft nucleophile. The sulfur is big, it's not negatively charged, but even if it was, that would still be soft. Goes to 1,4. We flip the negative charge, we flip the pi electrons up here to make the enolate. The enolate comes back down and gets protonated. Here are the protons that we've picked up from the second step of the mechanism. What's going to protonate it? Well, how about another molecule of our thiol? And there's our product. Note I'm using a little wiggly line to show that this would be a racemic mixture, as would this. So, hard nucleophile, 1,2, soft nucleophile, 1,4. Well, okay, we've kind of got that down now, maybe, but how does it all tie together with this reversibility and kinetic versus thermodynamic control and all that jazz? Figure 1716 tries to pull this all together, and it's a good figure, but it is also a little misleading and definitely can be confusing. So I want you to go ahead and give it a stab, but these are the important points that I want you to take home from figure 1716. Alright, first of all, Conjugate makes a point of saying that 1,2 addition is faster, leading to the kinetic product. You need to insert this phrase. That is because when you're using a hard nucleophile, that hard concentration of negative charge on the nucleophile is really attracted rapidly to the hard concentration of delta positive on the carbonyl carbon. So here's my conjugated system, here's my nucleophile, zoom it going straight to 1,2 because they're in love with each other and they are attracted to one another. Happy Valentine's Day. But that's not all. The 1,2 addition intermediate, that oxyanion here, well, you know, it's less stable than 1,4. Here's the 1,4 intermediate, because the charge is not delocalized. This charge is the enolate, so this guy is more stable than this guy, and you'll see that in figure 1716. Two more take-home points from that figure. 1,2 addition is faster when you're using a hard nucleophile, and it's not reversible. That's kind of the key, because you can't do the reverse reaction and kick out that Grignard reagent, or H- again. So if you think that once that R group adds to give you this intermediate, that you can like swing this puppy down and kick out that R group to give the reverse reaction, ooh, don't go there, because that's just not going to happen. And then finally, the 1,2 addition product. And we already looked at the 1,2 addition intermediate, but now we're talking about the 1,2 addition product. It's less stable than the 1,4 product because it doesn't have the CO double bond. And if I've told you once, I've told you 1,000 times. Well, that's not true. But I will emphasize again and again that any kind of XO double bond is a rock, a thermodynamic sink, a real driving force. Think about the Wittig and how the driving force for forming the alkene was the formation of the phosphorus oxygen double bond. Okay? So, I certainly don't want you to memorize 1716, and I think if you look at it too long and too hard, you might get confused. But do realize all of these relationships will help you understand the energetics of these reactions, and use the hard soft stuff to help you understand the outcome of these reactions. But wait, there's more. Lithium dialkylcuprates are yet one more organometallic that we can think of as R-, but they're soft. So you can add those to table 17.2 under the soft nucleophile, aka reversibly adding nucleophiles that lead to the 1,4 product. The good news is, even though the mechanism isn't well understood, we can do our usual kind of hand-waving cheating thing and say, well, we'll forget about this ion here and call this CH3-, even though it's definitely not the same as CH3 MgBr and not the same as CH3Li, but we'll call it CH3- anyway, and consider that it is a soft nucleophile, and that makes some sense because copper is a transition metal. If you look at the periodic table, look at lithium, look at magnesium, they're both much smaller and much more electropositive than copper. So organocuprates will add 1,4 to give you, well, I think you can probably figure out what the product is. That guy. And again, I've shown the stereochemistry is a wiggle to show you that it's both R and S. We're not going to talk about how these are prepared, but you can imagine that they are prepared from the alkyl halides, and we'll leave it at that. You basically go through the alkyl lithium and then add a copper salt to give you your R2CuLi. And so this R group can be just about anything. The bad news with lithium dialkylcuprates is that only one of these methyl groups is used. The rest of this reagent goes in the waste bottle, and so it's a terrible waste of carbons. Okay, so let's summarize this chapter 17 stuff. Lithium aluminum hydride, sodium borohydride, these are hard, and they will just add 1,2 to give the alcohol from the aldehyde or ketone. Our first introduction to organometallics, the organolithiums and Grignards, hard. They too add to the carbonyl 1,2 and they stick. So both of these irreversible, irreversible, 1, 2. The Wittig, that's also hard, and it is going to give you the alkene in place of the CO. There's, even if you have a conjugated system, the Wittig is going to give you attack right at the CO. So it's soft nucleophiles like cyanide, alkoxides, hydroxide, thiols, enolates, and lithium dialkylcuprates. They add to the soft beta carbon to give you the 1,4 product. The bottom line here is 1,2 versus 1,4 depends a lot on that metal counterion, and in these particular cases they're not spectators at all. They play an important role, and we just basically think of it in terms of hard or soft to predict the outcome. So that's it for chapter 17. We'll do the rest in class, and bring your synthetic thinking caps because we're going to have some fun.